Hi everybody, so this video lesson will be on phylogenetic analysis, how to draw a phylogenetic tree from Sanger sequencing data. This video will be a quick version of the tutorial to show you, for those of you who want to recap how to draw the tree with people with basic knowledge on how to do so. So I won't be going into technical stuff, only going to explain to you quickly how to draw the tree. So your first step would be to open your chromatograms in a Finch TV or another appropriate program. Okay, then you have your chromatograms like this. What I'm going to do is I'm going to zoom out of the sequence, and then I'm going to trim the ends um, based on the quality bars at the top, like that. So I trimmed the 5 and the 3 end residues. I'm going to select the entire sequence and I'm going to blast the sequence to identify the organism from the 16S data. So I blasted it by going to Edit and Mega Blast. You get a page such as this one with your sequence into the appropriate section and simply select Blast at the bottom. Okay, then you will obtain results such as this. You can see that the organism that this one, that isolate number 7 is the Bacillus cereus. So I'm going to note that, I'm going to write that down for when I've done drawing the tree. So once I've done that, the next part would be to export your .abi sequence as a FASTA format. So I'm going to File, Export DNA Sequence FASTA. I'm going to save it in the appropriate folder. So then I can exit this, so you don't have to save if you don't want to. Alright, the next part would be to open Mega 7. Okay, go to Align, Edit Build Alignment, and Create New Alignment. DNA, and there we go. Go to this folder icon on the right, upper hand right side. Okay, open your FASTA sequences. You should have trimmed the 5 and 3 prime residues of all your .abi chromatograms. So then you can obtain your FASTA sequences such as this, and you just open all of them at one time. And you get your sequences like that. Select all the sequences. Go to Align Selected Block by Cluster W, Align DNA. Only change this, the DNA weight matrix, to cluster W 1.6 and press OK. And done with the alignment. Now you have your sequences such as this, aligned perfectly. Now delete the 5 and the 3 end residues that have gaps in them, because we don't want one sequence to have more DNA information than the other. Do the same for the 5 prime end, like that. Delete that. Okay, so now we have all the sequences are the same length and they are aligned, right? Ideally you would go through the whole thing one by one and check everything, but we're not going to do that because this is a fast session. Now I'm going to export your alignment in mega format. On the desktop I'm going to save it as tree. Right, press OK, yes, exit this window, simply open your tree by double clicking on it where you saved it. Open the tree, go to models, find best DNA protein models to select the best algorithm for drawing your tree. Don't change anything here, just press compute. Now it's going to calculate which algorithm is the best one for drawing your phylogenetic tree. Okay, so in this case it's K2 plus G, and you look at the bottom what that means. It's K2 is this model over here, and plus G means plus gamma distribution, as it says over here, right there. Okay, so now you know, so note that. Exit this, go to phonology, construct test neighbor joining tree, say yes, right? put your test phonology to bootstrap method and change it to at least 1,000. The more the better. Change your model to the Chimera 2 parameter, or whichever one your model test told you to use, and remember to change whatever other parameters that also told you to change, for this case the gamma distributed as well. And then simply press compute. Right, and there you have your tree, like that. Okay, so now you should have blasted all of these sequences, so you should know what each of them are, and then you're going to use Paint or Photoshop or some other program that you can delete, or you can use Word as well, delete the isolate um, uh, names and fill in the species. So then you get something like this. From here you can see that the species group together, and here the genus group together. And another thing is the entire gram positives grouped together and the gram negatives grouped together. Now, the distance between species are measured by the horizontal distances. For example, this species, they're the same genus, the Bacillus cereus and the Bacillus subtilis, but they have this plus this distance between them. Here's a key. This tells you how many substitution nucleotide difference there are for this distance. You can see there's a big distance between the gram positives and gram negatives. And here you can see there's a little distance between these two Aromonas veroni species. So there's somewhere a strain difference between them. Okay, and that's it. Any other questions, please feel free to come and contact me and I'll help you with anything you may need.